Welcome to the quality control session. We will now look in detail at this approach. To explain this concept, I show it to you via a simple example of process control for a material discharge because of an out-of-spec event. Here you see a sketch of a direct compaction setup consisting of 2 feeders, a blender and a tablet press. After the blender, the API concentration is monitored via NIR. A discharge algorithm is implemented that triggers the discharge valve in case the material is regarded as out of specification. If now the NIR probe detects material that is out of spec and the discharge algorithm decides that the discharge valve should be opened, the powder is diverted to the waste after the blender. As the tablet press hopper is still full, it would continue to run. Another algorithm controls the fill level in the hopper of the tablet press. The algorithm controls the speed of the tablet press. This would be considered process control. You see, control is complex. For now, we stay with the example for quality control, so the discharge of out-of-spec material. The reasons for such an out-of-spec material discharge can be process disturbances like a feeder malfunction or feeder refill. The discharge can also be caused by raw material variations like a change in the moisture or a change in particle size distribution, and of course also due to material purity issues. In this example, the measurement position and the discharge valve are almost at the same location. However, if there is a significant distance between these 2 points, RTD models need to be used to track the material between the NIR and the discharge point. Keep in mind that the distance between the discharge point and the NIR probe also dictates the time you have to decide if the material is in spec or not. In this example, this would be only less than a second. Now let's move to another example. Material propagation is not only needed for quality control. You will also need to monitor your material propagation for batch definition, as you might remember from an earlier video. When running a continuous manufacturing line, it is requested to define a batch of produced material. In contrast to traditional batch manufacturing, the definition of such a final product batch is not unique. ICH topic Q7 says that the batch size can be defined either by fixed quantity or by the amount produced in a fixed time. No matter which of the approaches is taken, one needs to know which raw material batches are part of a final product batch. This sketch explains the idea of using RTD models for that purpose. On the top you see the example process consists of 3 unit operations. The formulation consists of 3 substances, R1, R2 and R3, which enter the process at 2 different unit operations. During the entire production campaign, 4 raw material batches of R1 in red, 3 raw material batches of R2 in green, and 2 raw material batches of R3 in yellow are used. At point 1, raw materials R1 and R2 enter the system. Using the residence time distribution between point 1 and 2, we can track the materials R1 and R2 and their batches, which are here highlighted with different shades of red and green. At point 2, raw material 3 is fed to the process. The RTD between points 2 and 3 is then used to track all raw material batches. After defining the final product batches based on a fixed time interval, we can identify which raw material batches are part of the final product batches. In the present example, 5 different raw material batches are part of final product batch 1, 8 for batch 2, and again 5 for batch 3. This information is crucial in the event of a recall, and it can help to optimize the batch size by reducing the number of raw material batches in the final product batch. With that, I'd like to thank you for your attention. See you soon when we continue to discuss basics of process control.